So now we go from capacitive sensing to magnetic sensors. The next paper is MIPOS, human body pose tracking using magnetic and inertial sensor fusing from CMU, and it will be presented by Riku Arakawa. If his notebook cooperates.
Okay. Hello, I'm Riku Arakawa, a PhD student from CMU. I'm happy to present our work, MI Poser. I worked on this project during summer internship at SNAP Research last summer. So, inside-out tracking of human body poses using common sensors holds significant potential, especially for AR and VR scenarios. For instance, immersive AR games or exercises users can enjoy with their body expressions. Existing inside-out systems typically adapt vision-based methods with handheld controllers. This approach prohibits hands-free and occlusion-robust interactions. Or there are also IMU-based approaches. For example, Deep Inertial Poser uses multiple IMU sensors on the body. Or our previous project, IMU Poser, uses common devices to reconstruct body pose. These solutions still suffer from insufficient accuracy or require densely distributed sensors. The goal of this project is to achieve a practical pose tracking system, particularly suited for body-centric AR scenarios. Such characteristics include accurate, hands-free for natural interactions with your hands, and occlusion-robust for dynamic body movements, and not power-hungry for resource-constrained devices. To this aim, we leverage electromagnetic field EMF sensing, which consists of EMF transmitter source and EMF receiver sensors using off-the-shelf 3D coils. EMF tracking enables precise 6 DOF tracking in the middle range, which is suitable for body scale tracking in concert with AR glasses visual inertial odometry. Several works have utilized EMF tracking for interactions. For example, Aura is VR controller tracking by embedding 3 coils in head-mount display and a set of orthogonal receivers in handheld devices with reasonable power consumption. Similar work to ours is EMPOSE, a wearable EMF-based body tracking system that uses 6 or 12 on-body sensors, which requires users to wear an additional EMF source on their back. Still, users need to wear more sensors on their body. And more importantly, although recognized, these EMF-based tracking systems are prone to be affected by metal interference, and no practical solution was established yet. We proposed a body tracking system specifically designed for AR scenarios that maintains accuracy using less sensors and robust to metal interference. I'll explain the body tracking part first, and then introduce our solution to the metal interference. MI Poser utilizes wrist-worn EMF sensors for tracking. As depicted in this figure, users wear an EMF receiver on each wrist, while an EMF source is mounted to the AR glasses. The EMF tracking captures the wrist poses relative to the EMF source. Simultaneously, the AR glasses can track the user's head position in the world coordinate based on visual inertial odometry. These sparse measurements are input to our IK model, inverse kinematics model, to reconstruct a high-fidelity upper body pose. We first examined its tracking performance by collecting a new dataset. We invited 10 participants and have them take different body poses while measuring their ground truth body pose with Kinect. The results across different joints and motions are presented in this figure. The overall position error is 6.6 centimeter. By examining the error by motions, larger errors arise from those involving fast and extensive torso movements, such as tennis swinging. Still, the overall error is reasonably small, including when hands are even out of view from the AR glasses. For comparison with prior work, we compared the performance of upper body tracking of our system with two other prior work based on IMU sensors, DIP IMU and IMU Poser. This is a position error. Note that this is just a reference since the dataset and also sensors used are different. It was suggested that MI poser achieves a good performance thanks to the precise tracking offered by the EMF sensors. This is a demo video. It can reconstruct a wide variety of body movements, such as jumping, punching, and swinging arms. Moreover, unlike existing wearable vision-based systems, MI poser is occlusion robust and thus enables tracking in a much wider range, unlocking new applications such as AR dancing with body expressions. Moreover, in using EMF tracking, metal interference is an inevitable and important issue. Thus, we propose metal interference mitigation, MIM, to enhance the input data of the pose reconstruction. This is demonstrating the metal interference effect. The tracking performance of the EMF sensor can get degraded by metal objects in the environment when they are close. Both its position and orientation are affected. Such errors causes IK model's failures, such as jittering and unsmooth artifact. Thus, to mitigate the interference issue, we propose two approaches based on EMF-IMU sensor fusion. If the interference is short, it is detected, and tracking is corrected using IMU sensors dynamically, like on the left. Now, on the other hand, if the interference is long, as in the right side, such as when a user holds a metal object, it is detected and can be used to inform users of the degraded performance of the tracking. The first part is interference detection. There are two values regarding the rotation of the sensor based on the different principles: angular momentum from the gyro sensor of IMU and orientation from the EMF sensor. If no interference occurs, an approximation holds. That is, the orientation coming from the EMF sensor is almost the same as the rotation odometer computed from the IMU sensor. So we take the difference between these two terms and use its error as an indicator for the interference. This is a demo. The estimated interference level is highly correlated with the tracking errors. The interference happens when the hands moves around metal objects, such as a room door, or holds metal objects, such as a can or a smartphone. We also propose a way to dynamically correct the trajectory and the interference with IMU sensors. This demo presents a user moving their hands horizontally over a metal object and illustrates the two outputs of the proposed method with and without MIM. Without MIM, the center part, the hand pose exhibits significant variance due to the interference. However, with MIM, the hand pose becomes more stable and the orientation appears more reasonable. Lastly, this is the system performance of MI poser. It works with relatively small power consumption. The metal interference mitigation and IK model does not cause significant delay, and end-to-end system runs efficiently at 60 Hz. In summary, we propose a practical solution for body tracking in AR scenarios using EMF sensors, while also proposing a solution for inherent metal interference mitigation. Let's discuss more at the poster session. Thank you.
Yeah, thank you very much for this nice presentation. So again, one question if you have one. Okay, Bo, yeah.
Because I see you have the sensor node on the wrist. What about the elbow and the shoulder joints? Are you using some method to predict this? Because you have the full upper body volume.
Yes.
How do you do the elbow and shoulder?
Yes, so the basically input is the wrist and head position. And for other joints, we trained machine learning model from existing dataset, specifically just AMAS dataset, and to estimate those plausible joint positions.
Okay. And just follow up to when you compare with the state of the art, are those including all the upper body joints or only the point you are tracking?
Yeah, to clarify that, we use the same sensor setup. So, for example, IMU poser, we used our wrist and head IMU data as an input. Only for the joint, yeah. So.
Okay, thank you very much again.
Thank you.
So, are the next presenters for post-sonic here in the room, right? So now we go from having done capacitive, then magnetic and IMU, to ultrasonic tracking. So the next paper is post-sonic 3D upper body pose estimation through egocentric acoustic sensing on smart glasses. And it's presented, I assume, by Saif Mohammed? Okay.
Thank you. Hi, everyone. I'm Saif. I'm a second-year PhD student at Cornell University. Today,